Hello everyone, welcome to JGCA Masterclass. Guys, in today's video, we are going to cover organolithium reagent, which you can see under organometallic compounds. And the topic is very important for all the students like BSc, MSc, CSIR NET GATE, and preparing for any competitive exams like IIT JAM. You can find many questions based on this topic. I have already recorded this video earlier in Hindi, but now on request I am recording it in English. And you can find many examples of molecules under organolithium reagent, and we will cover many examples. So now we'll see the very first application of organolithium. As the name suggests, organo means it has the organic part, and lithium. Organic means it is made up of carbon. So you will have a carbon lithium bond here. So it has many application, and the most important application is it is a very strong base. And the role of the base, we know it abstracts the acidic proton. So we'll take a general organolithium here. Organic part we will represent here with R, and this R can be any any alkyl group, CH3, ethyl or allyl or vinyl, any group it can be. So now we'll apply it to many other reagents. First we will see on water. So if you have water and organolithium, what happens? So as we know, lithium is electropositive, which carries a positive charge. So the carbon which is attached to it will have a negative charge on it, and so it will act as a nucleophile. And you can notice here on water, you have a hydrogen here, two hydrogens are there. So the oxygen being electronegative, it carries a negative charge. So the hydrogen will have a positive charge. So what happens, this nucleophile will take and abstract this proton, which is acting as a acidic because of having a electronegative species adjacent to it. So it will give you the hydrocarbon and LiOH formation. Next, if you have alcohols also you can notice here you have O, which is electronegative species. So hydrogen which is attached to it will be acidic proton, right? So acidic protons will be abstracted by this organolithium, and it will give you again hydrocarbon and LiOR. If you have aromatic alcohols, here again you can notice here that oxygen carries a negative charge which is in conjugation with the aromatic ring. So more stabilization is there. So this proton is more acidic. Higher the stabilization, higher the acidity of the proton. In that way you can find out the acidity and acidity order also. So this proton is acidic, and so the organolithium, since it acts as a base, will abstract this proton and will give you RH and LiOAR. So further these again will act as a nucleophile. You can apply it for the further chemical reaction. We will see later on. And now we will see the amines. Amines, again nitrogen having two hydrogen here. Because of its electronegativity, this is again acidic proton and will be abstracted and will give you here hydrocarbon and RNHLI. Acetylene. So acetylene, if you want to know whether this hydrogen is acidic or not, whether this reagent will work on acetylene, you can see here carbon will have a negative charge here, hydrogen being acidic positive charge, and this negative charge on the carbon, since it is sp hybridized, will be stable, and higher the stability, more acidity. So this hydrogen is stable, it's acidic proton, and so it will be abstracted by the organolithium, and it will give you the lithiated acetylene. So here lithium is carrying the positive charge, so this carbon on acetylene will have a negative charge and will act as a nucleophile for the further chemical reaction. So it is a better nucleophile compared to your acetylene. Now you have a tertiary butyl group here. So here hydrogen, you can notice here that this is a weak hydrogen, weak acidity proton, and since we know organolithium is a strong base, it can even abstract the weaker acidic proton also. So here again you can find this reaction in the same way like we have observed for the other cases. Next you have allene here. Allene, you can notice here it is sp2 hybridized, like we have noticed sp hybridized hydrogen. This is sp2 hybridized. Again acidity will be there because of the stabilization, and so you can find the reaction here as well. The hydrogen is acidic and will be abstracted by organolithium, and you can use this for the chemical reaction and it will act as a nucleophile. Now you have the compound which is having two sulfur, and in the center you are having CH2 group. So this CH2 we need to find out which is out of many proton present here, which proton is the most acidic. So if you see the carbon in the center of these two hydrogen, the bearing hydrogen, will be more acidic because of it is covered by two electronegative species, so will be more stable here and will be more acidic. So this proton is more acidic compared to the other protons, and so this part will be lithiated, and you can use it for the further chemical reaction where this carbon carries a negative charge, and you can use it as a nucleophile. So in all these cases we have seen that organolithium is acting as a strong base and will abstract the proton. Now we will see for some particular category of type of protons, like if you have allylic proton, you have benzylic proton, organolithium will give you the product here, while if you have done already a Grignard reagent, that doesn't work with allylic and benzylic substrate. So we will see here by taking the general example organolithium. You have a allylic substrate here. Allylic substrate is having 3 carbon, 1 double bond is there. So we want to know whether this proton which I have indicated is acidic or not. So if you abstract from this side, carbon will carries a negative charge, and this negative charge will be in resonance with the double bond, so it is stabilized, and so we can say thus allylic proton is acidic and will be abstracted by the organolithium. So R minus will take this proton and will form the hydrocarbon, and you get the lithiated substrate. So you can use it for the further chemical reaction as a nucleophile. Second, you have a toluene here, aromatic compound. Now we want to know the acidity of the proton, whether the aromatic proton or the CH3 proton are more acidic. So now you just see, if we consider the methyl, and we'll say that after abstraction of this proton, it is going to form a positive charge on CH2. So that is a benzylic proton or benzylic carbocation, and that is in resonance. So we can say this hydrogen on the methyl is acidic and will be abstracted compared to the aromatic proton because there is no conjugation. And so the CH2 will be lithiated here. You have another compound, cyclodipentene, you can see here. Now the center sp3 carbon, the proton which is present here will be acidic because after abstraction you can see here resonance presented. So basically to find the acidity of the proton, you can notice higher stabilization should be there, and here the stabilization is because of the conjugation, and so it is the acidic proton and it is lithiated, and you can use it for further chemical reaction as nucleophile. Here you have aromatic proton and you have here sp3 proton also, which is in the center, and if some abstract the proton from here, then it is having the more conjugation. More conjugation means higher stabilization and will be acidic, and you can notice the reaction here. Similarly, we have seen like toluene, same like toluene, you can find here CH3 proton will be lithiated, abstracted and lithiated. Now you have here terminal methyl, you have CH2 and you have CH2CH3. So we need to find out which is the active site for organolithium. So the most stable, we will see first here in the center of this CH2 which is present here. Once the hydrogen is abstracted, it will generate a carbanion and it is in conjugation with both the carbonyl. So higher stabilization is there compared to the terminal methyl because it is in conjugation only with one carbonyl. And so the central carbon will be lithiated and you can use it for the further chemical reaction. Next, with amines, you can notice here you have a CH3 proton here. You have CH also, and we know that the organolithium can act as a strong base, can act as a nucleophile. So, whenever the situation is like that, you can notice that and note down that if there is a competition between nucleophilicity and the strong base character of organolithium, it will first behave like a strong base. So here you have electrophilic center for the nucleophilic attack, and you have the proton here, which if you see that it is abstracted will form a carbocation and it is in conjugation here. So since conjugation is possible, first it is going to behave like a strong base and it will abstract the proton from here and it will form positive charge here, and because after conjugation the nitrogen will be lithiated because nitrogen compared to carbon is more electronegative. So the lithium being electropositive will attach to the nitrogen. Okay, so there is a competition between carbon where the carbon is going to lithiate on nitrogen. The one which is more electronegative will be lithiated here. So after conjugation you can notice this nitrogen is lithiated. So now you have isonitrile here, and here again you can see there is you have a proton which is present to the nitrogen adjacent, and it should be the most acidic as we have seen in the previous example. And you can have here conjugation as well. Both carbon is present, so which carbon is going to be lithiated? The terminal one, because we know the carbon, this carbon should be tetravalent, and you can notice here it is trivalent. So first of all, it is not unstable, it is stable because nitrogen here you can notice 4 bonds are there. So nitrogen should be trivalent. So I haven't drawn here. You can in that case can draw plus and minus on plus on the nitrogen and minus. So accordingly it will be balanced completely. So basically to form a 4 bond here, after resonance you can show the terminal carbon as a lithiated, and further chemical reaction you can show the chemical reaction with all these reagents which we have designed so far, right? All are after abstraction of a proton we are generating the active nucleophile which you can use for the further organic chemical reactions. So the second property and application of organolithium is it acts as a good nucleophile. So what is good nucleophile? That attacks on the electrophilic center. So you should have the condition is electrophilic center should be present along with the organolithium. So organolithium like R can be methyl, butyl, phenyl, any organic part you can have here. So you have organolithium and you have here aldehyde. You can notice carbonyl group is present where carbon is having a positive charge, oxygen having negative charge. So this carbonyl carbon is electrophilic center. Having a positive charge means it is electrophilic center. And we know R carries a negative and lithium positive. So basically this negative charge on the R nucleophile, this nucleophile will attack on the carbonyl carbon, and you can notice here it forms this compound, and after hydrolysis of this OLI you will get the alcohol here. So basically organolithium on aldehyde it converts into alcohols here. Similarly, if you have an aromatic like here previous case it was aldehyde, now you have ketone here. On ketone again it will behave like same like we have seen in aldehyde case, and it will convert it into alcohols. Cyclohexanone, this is again a ketone. In the same way you can show the attack of the nucleophile on the carbonyl carbon, and after hydrolysis it will give you alcohols. Acid halide, you can notice that this nucleophile will attack on the electrophilic center and followed by the loss of LiCl, because Cl being a good leaving group, it will release first and will show the loss of LiCl and formation of ketone here. And we know further, if the organolithium is in axis, it is given to you, then you can show the further chemical reaction of the organolithium on ketone, like we have shown here. So finally it will be converted into alcohol, but that you can show only once it is given in axis. That we will see later. In case of imine, you can notice again that in this type of example we have seen just in the previous case under strong base application. There it was CS3, now here it is pH. So there is no proton given here which can be abstracted, and so it will not act as a base here. Rather, you have a electrophilic center, so it will attack on the it will act as a nucleophile and will attack on the carbon, which is electrophilic center, and will be forming the nitrogen will be lithiated, and further hydrolysis it will convert into NH here. Nitrile, you can notice same way, nucleophilic attack will be there on the electrophilic center, and you can form this compound which on hydrolysis of imine will convert into ketone and ammonia. Here again, this is the active side. If further organolithium is present, you can show the chemical reaction and form the alcohol. You can notice we are we can see the application of organolithium on various functional group like aldehyde, ketone, acid halide, imines, nitriles, and now isonitriles. So all these function groups are very important and present in our organic molecules. All our pharma drugs are made up of having all these functional groups. So organolithium is really very important reagent for the organic chemical reactions. So isonitrile, same way you can show the chemical reaction here, and on the electrophilic center the organolithium will attack and will form the imine derivative, and further hydrolysis it will give you the product here. And further hydrolysis of imine, it will convert into amine and aldehyde. So like this you can show the chemical reaction, and you can whenever you have to design aldehyde or amines, you can select isonitriles and organolithium and design it. Here again we have, like I told you, whenever it is given in axis, what happens first, same it is going to attack on the electrophilic center, and after hydrolysis it will give you ketone, which is, if the axis of organolithium is given, again it is the active side and will convert into alcohols. Another important note is when you have sterically crowded ketone, there it can form the product, while Grignard reagent is fail in the sterically crowded condition. So this is again a sterically hindered lithium, organolithium, which will again attack on the this electrophilic site and will show you the product like we have seen in the previous case. So basically it can even attack on the highly sterically crowded electrophilic center. So organolithium is really very important reagent for organic chemistry. Now some you can notice here, if you have conjugated carbonyl, so far we have seen only carbonyl compound. Like in case if it is given to carbonyl, conjugated carbon, how does it behave? So let's take one example, and we will see here application of two more reagent and compare it with organolithium. So again it is important for competitive exams because this type of comparison comes in competitive exam. Whenever I'm talking about the comparison that Grignard reagent doesn't work and organolithium works, so this type of reactions are really important. Here again we will see this conjugated carbonyl, and you have organolithium given. H plus means after hydrolysis what happens. So here we know whenever the conjugated carbonyls are given, there are two type of addition can take place, either 1,2 addition or it can be 1,4 addition. Okay, 1, 2, 3, 4, 1,4 addition. So you have to note it down that whenever organolithium is present, the addition is 1,2. So directly you have to attack on the electrophilic carbon, and it will After hydrolysis, it will form the alcohol. Similarly, Grignard reagent also shows 1,2 addition, and same product you can notice here as well. But when you have dimethyl cuprate, lithiated cuprate, in the presence of acid, it shows the 1,4 addition. 1,4 addition you can notice here, and here you can notice at the fourth position only the carbon methyl group is attached, followed by the formation of alcohol, and since it is having the conjugation enolic form, it will convert into ketone. So from alpha beta unsaturated ketone to ketone it is designing with the help of organolithium. Okay, this lithiated cuprated. So whenever you have to convert alpha beta to ketone, then you can take the help of lithiated. Okay, so this is dimethyl cuprate. Third application is metal-halogen exchange. So like if alkyl halide is given to you in the presence of organolithium, what happens, as the name suggests, metal-halogen exchange. So the metal is going to take this halogen. Okay, so metal and halogen exchange means the lithium will come in place of X halogen and X will come in place of Li, and so the exchange is taking place and will form the alkyl halide here. We'll take one example here. You can notice you have here halide present on the organic molecule, and in the previous cases we haven't seen halide so far, and in the presence of organolithium, if it is given, we know that the exchange will take place. In the in place of Br, the Li will come. How? So we know Li carries a positive charge, Bu carries a negative charge. So it will attack and this bromine will be electrophilic because you have a electron withdrawing group. So basically this Br will act as a electrophilic. So positive charge it carries. So Bu will attack on this and followed by the formation of, okay, so this carbon will take a negative charge and will take so the lithium here. So alkyl halide is liberated. Similarly, you have aromatic halide here. Just whenever you see halide, you just exchange it with the lithium. That is the easiest thing you can show and you can form. So this again you are generating here the nucleophilic centers, the active site for the further chemical reaction. Br, you show the exchange and it will be lithiated and active for the further chemical reaction. Pyridine, just like benzene we have seen, same way you can just show the exchange, and now this is the active site, carbon carries here negative charge, and so it is acting as a nucleophile for the further chemical reaction. Br will be exchanged with Li. Important thing is the stereochemistry is here, the position of pH and Br is trans to each other, that will remain same. So here stereochemistry will be retained. If you have two bromine also, that in the presence of 2 moles of butyl lithium, both will be exchanged. Now the next application is ortholithiation. Ortholithiation means we have here aromatic compound. Ortho, meta and para comes whenever you have aromatic compound. So this is mono-substituted aromatic compound. Ortho position is next to it. So if we are doing ortholithiation, means the proton should be abstracted and it should be acidic in that case. And in the presence of butyl lithium, since OMe is an electron withdrawing group, and so it makes it acidic and it will be abstracted and will be lithiated here. So this butyl, which is carrying a negative charge, will take this hydrogen, okay, and will form a hydrocarbon, and this part is lithiated. So ortholithiated, and this is now active site, carbon carries a negative charge, so you can show any further chemical reaction on the ortho position. Here butyl lithium, we have to see which is the acidic proton here, the one which is next to the nitrogen, because nitrogen is electronegative. So the next hydrogen should be acidic to it and will be lithiated. Same way for with the thiophene, you can say the sulfur, the next okay, the 2 position, if you start the numbering from the sulfur, Okay, we always start with heteroatom. So the next two position will be active side because the proton is acidic and will be lithiated. If you have furane, oxygen in the 5-membered ring having a 2 double bond, so and the reagents are list is given butyl lithium to aldehyde and after hydrolysis. So step by step you have to go ahead. First is acidic proton, which is next to the oxygen, will be lithiated. Now it is the active side. Carbon is having a negative charge, will act as a nucleophile. You have an electrophilic center. So the reaction will take place like this, which will be OLI, and after hydrolysis it will form the alcohol. And so you can design the product in the same style. Now here you have CONE2, NET2, and the reagent is given butyl lithium, THF, and second is methyl iodide. So it works here at minus 78 degrees centigrade. Now we have to see now which role it is going to do here. So again, aromatic compound, we will see ortho-lithiation is given. So far we have done all reaction at ortho position. So here again we will see here this proton, whether it is acidic or not, which is adjacent to the this CONET2. And you can also see that you can that carbonyl is a carbon is electrophilic center. So as there is a competition between whether it will act as a nucleophile or a strong base, then we know that it will first act as a base. So this proton, which is adjacent to this carbonyl group, you can notice here the CONET2 is an electron withdrawing group, and so it will withdraw the electron and makes this ortho position proton as acidic, will be abstracted and lithiated. Now it is an active site, carbon carries a negative charge and it will attack on the methyl iodide and will be ortho substituted with the loss of lithium iodide. So now like this you can take the applications of butyl lithium. One very important and very good example, beautiful example you can say, you have here meta-di substituted aromatic compound, and you have butyl lithium. And if this is given to you, we know it acts as a base, it acts as a nucleophile also. So first we'll see the application here. Since we know it acts as a base first, so we'll find first the acidic proton. Now you have aromatic proton and you have here proton with the nitrogen also, which is more acidic. So if this nitrogen proton is going to be abstracted, it is in conjugation, not only with carbonyl, with the whole ring. So more conjugation is present. If this proton, which is in between the two functional group, if it is going to abstract it, it is only in conjugation with the carbonyl group. So the nitrogen proton is more acidic, and so it will be abstracted first, and you can form the lithiated nitrogen here. Second, since this is also acidic, you can show the abstraction of this aromatic proton as well. Now both are lithiated here. This nitrogen, you can show it is in conjugation, this negative charge, okay, and so it is stable. Now you have this lithiated, okay, aromatic carbon, which is having a negative charge here, okay, and so it will act as a nucleophile, and you have an electrophilic center. Same way you can show the chemical reaction, okay, it forms a alcohol like we have seen in the previous cases. Now one more beautiful thing here happening, because OH is having this oxygen is having a lone pair of electrons, so it will acting as a nucleophile here. You have an electrophilic center adjacent to it, so it will donate it electron, and followed by the loss of NHMe, it will form the cyclic product. So basically this cyclic product is designed in this particular course of manner, and the reaction is important. You can see in the competitive exam also. I hope you understood the concept of butyl lithium, organolithium, and its important applications in various fields. So see you in the next video. Happy learning.